Hi, everybody. Thank you for joining on time. My name is Paul Hagar. I am Executive Director of Safe Piping Matters. We're an organization that works to inform the building trade architects about important issues related to plumbing and piping systems. I want to start by thanking Sydney, especially and AIA East Bay, for inviting us to present today. We really appreciate the opportunity. Please also follow us on LinkedIn. We post updates twice a week on issues related to plumbing materials and systems. Here's the required AIA provider statement. I'll also take the opportunity right now to ask for feedback on this presentation. Most of these slides, this whole program came out of conversations with folks like you. For example, at a previous presentation, an architect suggested, this was a lot to digest, so please add a summary at the end. So we did that. So please do share input. I will put a link to the survey in our chat. Oh, that's not it. Well, I'll have to find it and then I'll post it right toward the end. So here's our learning objectives. This session is going to equip you to make informed choices about piping materials based on issues like health, safety, and sustainability. For example, we're going to talk about life cycle impacts. We're going to talk about fire risks and emerging research on leaching and even microplastics. So let's get started. We all know that plumbing and piping systems contribute in many ways to building performance. Today, though, we're going to focus on some issues that don't always get the focus they deserve: the effect of pipes on building sustainability and human health, as well as safety. A while back, an architect told me he spent more time thinking about urinal dividers than he did about piping. I guess that's understandable, but it's not really what we want to hear. So here's your key takeaway. Research shows that the types of pipe you use really do matter for building sustainability, health, and safety. We're going to cover the information today by going through 4 main sections. Each of them has some subtopics, and we're going to start with a quick overview of just plumbing systems to level set on what we're going to focus on. So the 3 applications that we focus on are supplying water for drinking and sanitary use, providing drain, waste, and vent systems to safely transport waste away from the building, and reducing risks from fires with sprinkler systems. There are, of course, other types of pipes in buildings, whether it's natural gas heating or electrical conduit, but we're not going to focus much on those today. So now let's talk about what types of materials are used for plumbing and piping systems, and a quick view as to why that matters. We mainly consider the 3 shown here: copper, iron, and steel, kind of 2 sides of the same coin, and pipes made of various types of plastic, which are used in a bunch of different ways throughout buildings. Each of these materials has strengths and weaknesses, as the chart starts to show, including different levels of stability, resilience, and performance. We're going to break down the details through the rest of this presentation. Here's a 4th box that shows some obsolete plumbing materials, of course, lead, galvanized steel, and polybutylene plastic. These pipes are no longer widely used, but we do like to mention them because they point to some interesting lessons that we can learn about what happens when piping systems fail. Lead, of course, has received lots of attention over the last 10 years or even before that, as various communities have struggled to deal with the toxic impacts of lead leaching. In the US, polybutylene pipes had a day of reckoning about 30 years ago, when weakness in the plastic started creating leaks. I think Australia actually is still dealing with that today. Galvanized pipes also pretty much qualify as a failed material because of the incidence of corrosion and failure associated with that. We need to also discuss the various plastics that are used in pipes, because there's a lot of different flavors. The main types used for building plumbing systems are shown here: CPVC, PVC, HDPE, PEX, and ABS. There's a quick table here that shows you some of the ways that they're applied in buildings, as well as some of a quick hit on what their advantage is and what one disadvantage might be. We're going to cover this in more detail again in later slides. So with that kind of basic setup, now let's look at sustainability considerations. And you may have heard that the construction sector is responsible for about 30% of the world's energy use and emissions, but construction is also responsible for a huge portion of resource use globally. For example, it's the second largest consumer of plastic and produces 17% of the world's plastic waste. If we want to become more sustainable, we got to keep improving the design of how we build homes, schools, and workplaces. The UN's been looking at this issue for decades. In 1987, so what is that, almost 40 years ago, they described sustainability practices really nicely, making sure that in the future, people will be able to live productive, healthy lives. That means moving away from things produced in a linear way, just consuming materials and creating trash, and towards circular processes. I'm a little more charged up on this today than I would be normally because I just got back from Greenbuild, and it's amazing to see all the people who are doing great work on this front. To understand what this means for piping and how the various types of piping stack up, let's take a look at what happens at all stages of this life cycle, from making the materials through installation and operation and after use. We'll do this on a material by material basis and start with copper. Copper has been used for hundreds of years in plumbing. Like all metals, you can see here the mining and smelting impacts the environment by disrupting the areas around mines and generating tailings and other waste products. There's a huge carbon footprint associated with refining that ore and producing the pipes. As we'll see in a minute, however, once that copper is made, it can essentially be used forever. Major copper producers, I think, have done a nice job of committing to publish their progress against UN Sustainable Development Goals, and implemented an independent copper mark program to track their progress. In use, copper piping performs really well. Lasts decades, often longer than the life of the building in which it's installed, and it's pretty stable and also repairable because you can solder and braze copper, making it possible to just take out a piece or replace a piece if necessary. It's probably its strongest point is what happens at the end of use. So here you can see this graphic on the right is meant to indicate the full energy associated with producing copper. Here's what happens when that copper is recycled. That energy footprint is reduced by about 85%. It's estimated about 2/3 of all copper ever extracted is still in circulation today. Life cycle of iron and steel pipe is pretty similar to copper. Mining and refining has impacts and produces a carbon footprint. And the heavier weight of iron and steel pipe also adds to that footprint because it increases the energy used to transport it. Also, like copper, however, the industry has engineered processes to gather pipes, reclaim the materials, and use them again. Percentages of recycled content, at least in domestically produced cast iron pipe, ranges up to 96%. Also, like copper, pretty stable material. And an actual advantage of the heavier weight of cast iron is its structural strength. So a lot of these pipes get buried or put under foundations or in parking garages. That makes them more resilient to things like impact or compression. At the end of the life, steel and iron pipes are two of the construction industry's most widely collected and reused materials. Recycling rates stand above 60%, according to the Iron and Steel Institute. The price per ton varies more than copper, but it's still significant, so people do recycle it. Finally, we'll take a quick look at plastic pipes. Again, the first part of this story has a lot of impact, just like for metals. So extracting natural gas or oil used for feedstock has big impact, especially on fence line communities like Louisiana's infamous Cancer Alley. Plastic comes from fossil fuels, so and once it goes into production, there are also problems, especially with PVC, because the production of PVC has been associated with forced labor practices in the Uyghur region of China. Plastic manufacturing has exploded over the last 30 years, and the UN projects that it's going to expand a further 5 times just by the end of this decade. What is that going to mean for the carbon footprint, and what is it going to mean for carbon waste? Those are some things we should be thinking about. In use, the many types of plastic make it a little more difficult to make sure that they are installed and maintained according to manufacturer requirements. We'll talk about that again in a few slides. Also, because plastic pipe is combustible, it has to be installed with more protection against fire risks, and we're going to talk about that as well. Here's the most significant difference of plastic pipes at the end of product life. Virtually all plastic is engineered for single use. That includes building materials. And the recycling rate for plastic pipes isn't 2/3, it's not 60%, it's virtually 0. So all that plastic either gets landfilled, adding to plastic pollution, or it gets incinerated, increasing carbon and emissions. You might have heard some claims from some plastic building materials manufacturers that the embodied carbon of plastic is actually lower than that of some metal products. I think they've reached that conclusion by excluding all the pre-production impacts of their material and all the post-use impacts of the material on the environment after it gets into landfill or gets incinerated. So this is the real area of difference. Copper, iron, and steel are circular by their nature, and they actually are handled in a circular manner by and large. As plastics are engineered and produced today, pipes made of PVC, PEX, and other plastics are just not circular at all. They're linear. During use, plumbing systems need to ensure, obviously, water quality is sufficient to protect human health. And the 2 pieces of research we track most significantly are leaching from pipes into water and the increasing aging of water inside pipes. So we'll take a look at that. Chemical interactions between piping materials and water, typically this is oxidation or chemical reactions. It means all pipes leach substances into water to some degree. Some materials are safer than others, and there are tools out there that rate that level of safety. I can just name one, happened to have been on a webinar this morning from a company or an organization called Habitable. It's habitablefuture.org. They had a really nice presentation on plastic building materials in buildings. There's a tool out there called Red to Green by a company called Materially Better. They do a nice job of scoring and ranking different materials against each other, not just piping, everything. So take a look at either one of those, and I'm happy to share information on those later. So we'll start with kind of the poster boy for leaching on this front, lead. It's obviously emerged as a serious public health threat. Flint, Newark, New Jersey, Washington, D.C., Chicago, many other communities across the country have been affected by lead leaching. It's not as prevalent in California. You guys have a lot more plastic out in your region, but it's still a really significant problem for individual families, companies, and communities to deal with. That's one of the reasons that the Inflation Reduction Act marked about $15 billion to replace these plastic pipes. Sorry, these lead pipes, my bad. So let's take a quick look at the other forms of leaching that occur from pipes. Copper does leach at relatively low levels, about 94% lower than what the EPA considers an unsafe limit. Also, you may know that copper is present in a lot of nuts and chocolate, et cetera, and it forms a role in muscle function. So for most people, the exception being folks with a syndrome called Wilson's disease, you don't have to worry much about copper exposure because your body just flushes it out. Similar story for iron and steel. They may begin to corrode at some point during use, and if there's a disruption to piping systems, I don't know, construction or renovation, you can end up with brownish water. And the industry kind of calls the limit on iron as a aesthetic limit because it ends up with this nasty brown color. And at super high levels, if someone was taking, for example, an iron supplement and drinking, brown water, they might get sick to their stomach. Turning now to plastic, microplastics are getting increasing attention as an emerging contaminant in water. A recent paper looking at plastic pipes out of Europe looked at microplastics exposure coming from plastic pipes after water treatment as water was flowing to homes and other endpoints of use. And they found that chemical interactions with water or microbial activity produced pitting on the inside of plastic pipes and shed significant releases of plastic particles into drinking water. A report on this research that's on our website actually looks at a summary of this research, gives you some images from the paper itself, and talks about associated health studies that talk about the effects of microplastics on the gut, the lungs, the nervous system, and reproductive system as well. Leaching from plastic pipes, in this case, chemical leaching, is well documented. CPVC, HPE, PVC and PEX plastic pipes, they're made of these complex blends of hydrocarbons, chemicals, other additives to make them stable, to put color in them, to make them UV resistant, et cetera. And these chemicals do leach from pipe walls over time. Gradient published a study in 2018 cataloging 163 leachates, that's substances that come out of the pipe that go into water, including VOCs, SVOCs, endocrine disruptors, and carcinogens. A troubling trend that we as humans are seeing is that as our exposure to chemicals increases, one symptom of the effect of that is that researchers are seeing severe reductions in sperm count over the decades, and those reductions correlate roughly to the increase in plastic use in our daily lives. Of course, we can't say how much of that comes from plastic pipes, but there's an additive effect, and we should be thinking about that. Now let's turn to water aging. This is another emerging topic of discussion in the plumbing industry, and here's why. A lot of the standards that were created for sizing of pipes to provide adequate volume of water to fixtures and appliances in buildings were created decades ago, and they essentially haven't been updated since. So water engineers are increasingly finding that potable water is aging beyond the 24-hour cycle and the 19-day test period specified by NSF ANSI 61, which is the standard that is used to measure the safety of materials used in pipes. Ironically, this challenge is actually exacerbated as buildings get smarter about how they use water. Because now we have low flow fixtures, we're specifying appliances that are extra efficient with water. So what this means is if you have an issue with the way your water system is designed, or if you have a building that's used only intermittently, think of a school or a vacation home or something like that, if they're sitting idle for periods of days, weeks, and months, that can be a problem. So IAPMO, which is the International Association of Plumbing Professionals, is increasingly calling now for, and they've created a tool, which I'll share in a second, that basically says you can downsize pipes and you should be downsizing pipes to make sure that the water is not over aging in a building. Here's why, because you get this increased effect of leaching as water sits in the pipe. It also gives a chance for microbes to grow more. So just talking about microbes, this is a nice graphic that Contractor Magazine put together, showing that these microbial colonies expand really quickly. They reach 80 times their initial level in water stagnated just overnight, and 40,000 times in water stagnated for 60 days. So like the length of a school vacation. So I think one illustration of this is that there was a spike in Legionnaire's disease as we transitioned out of the pandemic and the shutdowns associated with that. So I think unaddressed, either of these problems can cause, at the very least, taste and odor issues if you ever had that fishy taste or smell from water. But if it's carried further and the water doesn't get flushed out, it can threaten the health of occupants. Here's that tool I was talking about before, the iapmo.org water demand calculator. They published these new sizing standards way back in 2018. I think it's an interesting thing for you guys to look at because smaller diameter pipes, number one, they cost less, they require less support, and it will actually aid performance of buildings, safety of buildings, because it's going to allow the water to flow through more quickly. So our last two topics that we're going to talk about before we open up for questions deal with building safety. I end with this one because it's the one that kind of takes the most time and is in many ways the most important. So we're going to take a look now at how pipe materials react differently when accidents or disaster impacts happen in and around buildings. So some of the most serious damage from piping failures can come from chemical compatibility problems. So if you think back to what we were talking about in terms of failed plumbing materials, this was the issue that killed polybutylene pipes. They had interactions with chemicals. The polybutylene plastic had interactions with chemicals that created brittleness and stress cracking. And basically these pipes failed from the inside, and all of a sudden people had major leaks in their homes or in office buildings, et cetera. So these incidents, though, can occur from many different sources, and they're affected by a bunch of variables. So could occur from maintenance, could occur from a building occupant if they're putting something nasty down the drain. And what ends up happening is that over time, these pipe materials get impacted, they start wearing away, and the impacts vary again by the type of material. So again, talking about piping materials, it really does matter for this kind of system. So we're going to go through each one. Copper water is susceptible to pitting from water with aggressive alkaline chemistry. So here you can see kind of a cross section and this rough surface on the inside. Primarily, this aggressive alkaline chemistry occurs in the West. So Southern California, Arizona, and Utah. Most municipal water systems, commercial water systems, are going to be treating for this and mitigating that factor. But for untreated well water or small private water systems, sometimes they don't manage this well. I'm aware of at least one incident in Steamboat Springs, Colorado, where a major hotel has had pinhole leaks from copper because they didn't treat the water correctly. Iron and steel pipe, probably even more resilient to damage from the chemistry of water than copper, which is, both these things are pretty stable, but in extraordinary circumstances, they can be damaged. The one incident where where iron needs to be protected is if in a highly acidic application, like an industrial application. So here you can see a batch of epoxy coated cast iron pipes. Plastic, because there's so many different flavors of plastic, it varies in its chemical stability, just like it varies in the best way to use it or its resistance to temperature or whatever. What this means is that you have to really know what material type you're looking at, and even what subtype of material you're looking at. Is it PEX A or is it PEX B? What type of PVC is it? And for each one of these types of pipe, manufacturers list dozens of substances you should be avoiding in how you install and what you use around and put through these pipes. The lists are just far too many to go through today. I'll give you a quick sample of them, but it's a lot. So what's also hard to judge is that the speed and degree of damage done can vary a lot too. So there's sort of no rule of thumb. You just have to be generally careful. Bottom line, what this means is that the construction teams, the installation teams, your subs have got to be pretty careful. And the maintenance teams also have to be instructed to be careful as well. And I'll talk a little bit about one example of a couple Miami condominiums where this caused a problem. So here's a quick summary of things that can affect the integrity of plastic piping. Chemical used for termite treatment, mold abatement, those can cause brittleness or stress cracking. Other commonly used substances like caulk, solder flux, spray foam insulation, HVAC chemicals, fire stopping products, thread sealants, primers, cleaners. I mean, if you're starting to think plenum on this and why that might be an issue with some of these materials that are on the list, yes, that's an issue, because plenum spaces are tight and it's easy to have an issue. Other strong solvents, obviously oxidants, acids, bases, halogens, the things that are going to affect, metal pipes will also affect plastic pipes in general. If plastic pipes are stored incorrectly outside, or even if they're sitting on a truck outside for a long time, some types of plastic pipe will be affected by UV, weakening them. That would be especially important for long runs of plastic pipe. To make sure that they're adequately supported. And one thing that I learned from an architect who was on one of these presentations is that he ran into a problem with network cabling. So a sub, all the piping's installed in the building nicely through the walls, et cetera, and a sub came in to install network computer cabling and said, oh, here's my holes, I'm just going to run my network cabling straight through those. But network cabling obviously has to be really bendy, so they have a lot of plasticizers in the coating. And what ended up happening is that these wires were sitting right up against the pipes, and over time the plasticizers ate through the pipes and created these wormholes in the pipes, and obviously leaks and lots of problems. Switching from chemical compatibility to material strength, thermal effects can represent another form of stress that gets placed on piping materials. Expansion and contraction with long pipe runs with various temperatures can affect joints and fittings. It can affect fire stop brackets as these pipes are trying to move as they get warmer or colder. We can talk a little bit more about fire stops in a minute. Looking at this on a material basis, in this case, cast iron performs best. That's followed by steel and copper. And PVC and PE, because they're less dense materials, perhaps, they expand and contract much more significantly. What this means for you is that when you're designing the piping systems, especially these long runs in a stack or in an unconditioned space, like an exterior wall or a shaft or something, you need to think about what's going to happen to those pipes as the temperature changes during a day or in different seasons of the year. So you could also, in this case, consider using a more stable material in those kinds of applications. So we're also going to talk a little bit right now about permeation. Not generally an issue inside of buildings, but if you have a multi-building campus, you might want to think about this one, because piping that connects buildings on a campus or that runs from a building to the water mains often usually passes below ground. Might be under a street, might be through soil that contains pollutants. And research shows that some pipes allow these substances to pass through the piping walls fairly easily. This is called permeation. So the little graphic here kind of shows some instances where that might happen, from a nearby industrial location, a gas station. That's the thing shown sort of here on the graphic. Gas is one of the most frequently spilled pollutants that gets down into soil and water. The EPA says risks from permeation are limited to non-metallic materials, in this case plastic, because they are porous. So if you have a building that's located near a manufacturing facility, a gas station, agricultural location, things like that, you might want to consider the ongoing risk from leaks or spills and specify piping materials appropriate to protect against those threats. I mean, a recent example from, a year or so ago was East Palestine, Ohio. Those folks are unfortunately not sure why the decision was made to dump all that vinyl chloride into the soil and burn it. Some of it got burned and released into the air and caused its own set of problems, but the stuff that didn't burn passed into the soil. Those folks are going to have to be testing for months, if not years, as that material moves through parts of the aquifer and through the soil. Another incident near an Air Force base in Hawaii had a similar effect on, in this case, base housing in nearby communities. So families and businesses in these kinds of affected areas need to remain super vigilant, especially if they have plastic piping. So next, we're going to talk about fire. The main difference in fire risks. I'm missing a slide here. That's weird. Okay. Generally, what I say is the main difference in fire comes down to combustibility, and that is obviously related to temperature. If a structural fire or a wildfire occurs that affects that building or a community. So as a matter of reference, an average structural fire generates temperatures up to about 1,500 degrees Fahrenheit. Metal pipes are not combustible at this level, although they will obviously melt if they're exposed to very extreme heat. By contrast, we can see that plastic pipes burn at much lower temperatures than happen in a fire, starting around 400 degrees Fahrenheit. And some plastic pipes will also lose structural integrity and start to melt before they burn. And that can create other issues, including failures in exposed spaces, let's say under a sink or in walls that are exposed to heat, to flames moving up. We should also talk a little bit about chemical leaching from plastic pipes that get exposed to heat or that burn. One from not so far from you guys in Santa Rosa was a pretty good example of this in real life, where a wildfire burned several miles of a polyethylene pipe that supplied water to thousands of residents in the area. So obviously the plastic pipe burned. You can see that there. I'm not sure why they decided to put combustible plastic pipe above ground in a wildfire-prone area, but they did. What ended up happening is that not only did the people who were served by this pipe lose access to water for months, what they also discovered is that as this pipe burned, it leached benzene into the water, which then flowed into their homes, got on into their plumbing systems, and it either had to be, well, they tried to flush it out, but essentially a lot of these systems ended up having to be replaced. I wish I could tell you the story had a happy ending. For some reason, the community decided after this fire to again use plastic pipe for the supply line. Hopefully they buried it this time. I guess that was a value engineering decision. I'm not sure what's going to happen the next time there's a wildfire in this area. We'll see. This, by the way, applies across the board to plastic materials and buildings. And here's a great illustration from research showing why combustibility matters. The Fire Safety Research Institute has a couple of times done a really interesting study where they build two test burn rooms, one that contains natural materials, that's the one on the left, like metal, wood, wool, natural batting materials, natural fabrics. The other one uses more modern materials like plastic foams, polyester, vinyl wallpaper, etc. And they do a burn test on it. And even with the fire retardants built into the plastics, the time to flash over, so the time to when a fire has fully engulfed a room, was 3 minutes and 48 seconds for the synthetic room. That doesn't give much time for occupants to get out, and it gives almost no time for first responders, firefighters to get in and get that fire out. You should also notice that the smoke there is like kind of black, evil looking smoke on the right-hand side. This is a really interesting, if you can find it, well, look it up, it's easy to find. There's a YouTube video on that shows this like time-lapse fire catching and burning. It's pretty amazing. On the right or on the left-hand side, you can see that the natural fire at the natural room at the same timestamp was barely burning. And it didn't reach flashover for 29 minutes. That's a lot longer for the fire trucks to get on site. And the reason I say this is because plastic pipes are also made of plastic. And as we saw from the chart, they will burn. So if that's going to start with exposed pipes, but then it can spread into walls and upper floors of a structure. So I'm running a little short on time, so I'm going to kind of go through the next slides a little more quickly. Here are some of the chemicals that research has found get emitted from plastic pipes when they get extremely heated or burn. So you can see benzene there, which I mentioned before, carbon monoxide, formaldehyde, nice chemicals like hydrogen cyanide, sulfur dioxide, etc. Purdue has a Center for Plumbing Safety run by Professor Andrew Welton that studies what gets released into water from melted and burned plastic pipes. When he looked at wildfire areas after the wildfire had passed through, he found carcinogenic benzene levels 40,000 times above the safe limit. That obviously affects not only people who are in the buildings, but the firefighters going in to put those fires out. I've done a little work with firefighters who are struggling with increasing incidence of cancer. You can see this graph shows the growth in cancer rates with firefighters, roughly again corresponding to what I call increased plasticization of the built environment. Right now, 2 out of 3 active deaths of active firefighters in active duty occur from cancer, not accidents during a fire. I think that raises a question: should we continue putting this much plastic into the environments where we live and work? I'm going to end here kind of with a topic, fire stopping. We all know what fire stops are, but I just stick it there, stick a definition there so we all understand that these are systems that are meant to restore the integrity of firewalls. If these devices are going to work, every single one of them needs to account for the specific materials used for the pipe, the materials used for the wall, and the situations that they're designed to protect from. Fire codes obviously prescribe exact formulas for installation, as do manufacturer instructions. In reality, I've talked to several fire stopping experts who, when they go in the field, they see a lot of errors, including the one shown on this slide. For example, here you see a PVC pipe installed with a collar, copper and steel on flanking penetrations. What's wrong with this picture is that the collar that's meant to secure this pipe to the wall doesn't have fasteners that secure it, that actually will attach it to the wall and keep it there. Why that's important is that inside that cavity, inside the wall, I'll show you this in a second. Actually, I'll show it to you now. Inside that wall, this is intumescent material that when this pipe burns and starts to heat this material expands and crushes in on the pipe because it's the only area where it can close off. It can't push out on the collars if they're correctly installed. And that seals off the hole and prevents the fire from passing through that penetration to the other side, to the adjacent room or the adjacent floor if that penetration was running vertically. That's different than for non-combustible pipes, because in those cases, the fire stops don't have to account for the pipe burning. So they only have to account for the gaps around the pipe. A fire stop for plastic pipes has to account for the entire space, the space around the pipe and the space occupied by the pipe itself. So these types of installations are more complicated, and in reality, fire stopping experts say that they see a lot more errors with them. For example, using a drywall screw instead of a specialized fastener. That would be a good indication of an error that those guys would see. So we're almost to the end. I've left about 10 minutes for Q&A, but I'll quickly go through a summary. The first thing to say is that all pipes have impacts in manufacturing. That was kind of the life cycle thing that we talked about at the beginning. The biggest difference here is circularity after use. On the health side, chemicals from plastic pipes are the ones with the most serious questions around them about exposures. And in many cases, the effects of the chemicals that are in these pipes have not been sufficiently measured. And also we should talk about water age and mention that in this case, copper can outperform plastic in reducing the effect of microbial growth and biofilms. On the strength and stability side, if you've specified plastic pipes of a particular type, it's important that the subs and the maintenance folks understand what the risks are around the installation and maintenance, what substances can be used around those pipes. And also you need to account for thermal issues, expansion and contraction in unconditioned spaces. And for fire safety, I just talked about this, so I'm not going to spend too much time on it, but make sure that they're specified correctly using the right assemblies and that they are installed correctly to maintain integrity around penetrations. In this case, combustibility really does matter. So that's kind of it. Thank you again for letting me speak with you. I really appreciate your time. If you would like any more details on these issues, please consider downloading any of our reports. We have several reports on a bunch of different topics related to plumbing systems. from microplastics to the plumbing specification guide. And that's on our safepipingmatters.org website. Happy to email you the link afterward if Sydney gives me your addresses. And you can find, let me see if I can copy this. I think I can copy this now. I'll put a copy of the survey in the chat. Let me see if I can figure out how to do this. Oh, it still wants to get me to give you the Zoom thing. All right, I'll send that to you in a second. While we're opening it up for questions. So would anyone like to ask any follow-up questions in the time? I guess we have about 10 minutes left. Okay, well, while you're thinking, one question I sometimes get is, does piping really matter in the overall sustainability of a building? And to answer that, I can talk a little bit to a number that Habitable, the organization I mentioned earlier in the call, presented just today during a webinar that they did on plastics in buildings. Piping represents about 45% of the PVC used in a typical building. So this is a problematic material that's been on the red list for decades at this point, and it's still being specified at a high rate in piping systems and buildings. So this is definitely an area where if you're looking to not just impact sustainability, but also impact health and safety, I would ask some hard questions about performance on those plastic materials that are being used for those piping systems. Any other questions? Okay, just bear with me 1 second. I finally got this link, so I'm putting it in the chat right now. So just click through on this. Also, please, oh, here we go. Any hints on or upcoming trends regarding traditional materials like vitrified? Oh, that's a great question. That's really interesting because just today I got an email from a guy I've been talking to oh, you're welcome, by the way. I've been talking to a guy in Phoenix, a pipe manufacturer, and he's been getting some pressure from the municipality to replace the vitrified clay pipe with, which is what they've traditionally used. And it's obviously expensive, it's heavy, lasts forever. I mean, really, in that case, I didn't talk about it today because it's, a pretty small piece of the market, but it is for infrastructure piping, it's one of the best choices there is if you can afford it and you want something that's going to last like hundreds of years. I can't say I would expect this to be a trend of growth. But what I would say is you might not see people switching to PVC or polyethylene pipes sort of without some hard conversation because they've seen some of the issues that have come when those decisions have been made. In some cases, failures, especially in an environment like Phoenix, where you get those extreme temperatures, they can see failures fairly quickly. So hopefully a slowing of transitions to plastic. I don't know what's going to happen with clay pipes. I haven't really studied that much, to be honest. That's a really great. So the next question is, why are the codes not addressing plastic PVC pipe issue when it? If you look at, there's an organization that put out a report. Organization is called Beyond Plastics that put out a report on. They were targeting use of PVC pipes not inside buildings, but again outside. In this case, for the lead service line replacement. They have a really interesting analysis of Beyond Plastics is led by a former director of the EPA, and Judith Enck. She's super smart on plastic overall. She has a really interesting analysis of the ways in which plastic pipe manufacturers have gotten onto the codes and standards boards and influenced the way these codes get written. A couple of years ago, we were working on Capitol Hill against a proposal by the plastic pipe industry to encourage and incentivize use of innovative materials in piping systems. By their definition, innovative materials meant new materials, not the old traditional stuff like copper and iron or vitrified clay. I think probably the main reason that you don't see codes handling this issue in the way it needs to is that plastic pipe companies have affected the process. In some cases, municipalities, particularly those with really strong fire codes like Boston, New York, Chicago, Philadelphia, I think Kansas City is also pretty strong on this. They don't allow plastic pipes to be used in buildings over a certain height. And they don't allow plastic pipes to be used in applications like hospitals or schools, because they don't want to put those populations that can't evacuate quickly at risk. Another thing, I didn't talk about it today, but it's in our fire stopping report. Another thing to look out for, and it's sort of an example of the way that the plastic pipe industry has manipulated codes and standards to their benefit, is that there's a standard out there called the E84 flame and smoke spread test. You'll see some plastic pipe manufacturers saying that they pass a modified E84 test. What that means is, E84 specifies a particular way that you have to support the pipe, a particular way that you have to do the testing. They use a different form of support, or they support it, in some cases, they support it less so that the flame doesn't spread as much. In some cases, they put a substance in the pipe, which is not something that is allowed by the test. And then they publish their results as a pass on a modified E84 test. So if you see that, like, that's not kosher. Like, pay attention to that. So, and if you want more details, it's in our fire stopping report. Thanks for that. Braidless steel and stainless steel water canoe. Oh boy. Wow. That's a tough one. I haven't seen that one. I have braided stainless steel water connectors on my washer and dryer, so I'm hoping that's not a widespread issue. I'm going to guess maybe installation issue, maybe failure of the washer, maybe failure of a fitting. Those are, I don't know. If a lot of damage was done to the point where the insurance company was involved, insurance companies are increasingly looking at, because piping failures are such a high contributor to water damage claims, insurance companies are increasing, especially on the commercial side, they're looking at the materials and installation methods used for piping systems. Isn't stainless less flexible than regular? I'm not sure. Sorry, don't know. But braided stainless steel should be very flexible, like that's at least the stuff I use in the washer and dryer, like you can bend the stuff like by hand. Great question. I'm going to write it down. David, I will either hit you on LinkedIn, or I'll get Sydney to give me your I'll ask my technical guy about that one. That's an interesting one. I'll also ask about the flexibility issue. Any other questions? Great questions. Thank you. And please, I did put the link in the chat, didn't I? Survey link. Yeah, good. So please fill out the survey. Any other questions? Super. Well, thanks a lot. Oh, we have a couple of water leaks. Oh, yes. Well, really, I'd be curious to know what the issue with the plastic pipe aging was, and also how old the plastic pipe was. Plastic pipe manufacturers claim 50 years, maybe not across the board, but in general, that's what they claim. I sat in on the MEP 2040. I was just at Greenbuild last week. I sat in on the MEP 2040 presentation, which focused mostly on mechanical systems and refrigerants, as you might expect, but they did talk a little bit about pipes. And one of the interesting things, yeah, 20 years, there you go. That jives with what I heard, what I was just about to say, I heard in the presentation, which is in their calculations of embodied carbon, when they looked at piping, primarily plastic piping systems, they figured that that piping systems would be replaced 2 to 3 times during the average life of the building, which, let's remember that their baseline is about 60 years. So that jives with what you're seeing with plastic pipes failing in 20 years. All right, guys, please hit me up on via email or on the website if you have any other questions. And I really appreciate your time. I appreciate this is the best batch of questions I've had in a while. So thanks again for that. Really great. Have a great day.